Okay, hello guys. Oops, sorry. What the? Mm. Okay, hello. Let's start the sessions. So, first of all, I'm sorry that we have to have an online meeting like this for the class. Actually, I favor the offline class more than this one, but because your class has been some additional slot in my schedule, therefore I have no other way but to meet you online. All right, so hopefully that we can work it out this semester and you can find some good information about the course. Now, the thing I want to make sure that we all on the same page is that you guys interested in machine learning, right? In general, I hope so. And is there anyone in the last year or third year? Can you give me some sort of information? Because I literally have no information about that. So anyone here in the last year?
Yes, teacher.
You won? Okay. How about the others?
I'm also the last year.
Okay. Okay. So are you guys working on capstone projects? I mean, your graduation projects related to machine learning?
Yes, teacher.
For sure. Okay. The reason why I'm asking this is because it's the fact that when you choose machine learning and AI in general for your career, then probably at the time you enter the last year, you already have all kind of knowledge about machine learning. And that's concern me because the purpose of this course is to give you all kind of knowledge about machine learning. But at the moment you study this course, you are about to graduate. So you are a little bit odd for me to teach you something that maybe some of you already knows. Okay, so that is why I concern about your situations. But anyway, put that aside. The thing we are doing here is to propose some sort of idea about machine learning, and hopefully you can look at the journey of the course and gather some basic background of machine learning for your work. But by no means I'm saying that studying the course gives you a lot of benefit in your graduation projects. But anyway, we have to read a lot of paper in the future, so I'm open to discussions if you guys want to discuss some topics related to papers if you want to. Okay, just raise your hand and may I give you some advice on that. Okay. So today we are going to discuss about some basic of machine learning and hopefully that give you enough information for the topics. All right, let's start. So the questions we have at the moment we enter the course is that what's machine learning? Why do we learning this one? Why is so hard and why people so exciting about this kind of thing? Well, this has a long history, right? Machine learning is not some kind of new technologies. It has been there for decades. The problem is that nowadays we have the technologies give us a lot of strong computer, GPU, for example. And from that point of view, what you see is that giving a strong computer with GPU, you can train machine learning algorithms more efficiently, right? And that is why we need to study machine learning in general to see how do we come from some classical approach where the resource is limited into a big models of neural network that training on a massive machine with huge GPU, right? And so the questions of machine learning has been there for a while, and that definition has been defined long time ago. Back then, if I recall, it was in 1959. That was a very long time ago. If you see, oops, what's that? Anyway, you see that back then, about 60 years ago, they already have that kind of definition. They say that machine learning is a field of study that gives computer ability to learn without explicitly programming. Well, that gives you a sense of machine learning, right? You don't write code with a lot of if, else, for loop to do things. Just let the data write your programs in a way so that it can make decision on its own. Well, that idea comes to another level when Tom Michael have a formal definition of machine learning. Well, he said that a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance and at a task T measured by P improve with experience E. Well, a long sentence, right? Very formal defined. But in short, what you say is that we have some task T, right? Like recognitions or generation, for example, or reconstruction, for example. We have a lot of way to define the task. So the task here is so general. If you are dealing with a problem of recognition, for example, I want to recognize what kind of picture I'm looking at, then that task is classification task, right? Then for that task, what kind of performance measure you use? Maybe that is error rate, or may you concern about accuracy. So whatever you choose, that's performance P, right? It's measure how good the RM works on the problems. And then given experience, what is experience? That's just your data, okay? Whatever you see in the data is experience. So assuming that I have more data give you more information. So you should better have a higher performance in the same task. Okay, so that's the formal definitions of machine learning. And I think everyone can get that idea easily, right? So now, uh, this is another definitions of machine learning. Very briefly, machine learning is a way of constructing a programs that automatically improve with experience, and that's the thing. So there's a lot of study in machine learning. They may study some algorithms to build the programs, or they may do some sort of study on the theory of statistics. In case you don't know, there are some books that work on machine learning, but based solely on the statistic, and that's pretty interesting if you love statistic, I suppose. But now let me give you a book. Wait a minute. See, this has been a long time. I didn't check that book. It's a very nice book, but hard to read overall. So it's there. Where's the? Oh, no, it's wrong. Let's see. Searching for this. Wait. Okay, I got it here. So let me show you the link. Okay, so this one box teach you about machine learning, but not in the way that normal people will look. It's all about statistics. So machine learning is nothing but a bunch of formula related to statistics, conditional probability, Bayesians, theorems, and so on. So we also have some discussion about that in this course, so don't worry, it will come up in a few days later. So we have that. Okay, so you may want to take a look at that book if you love math, but if you don't, then fine. Just follow my material. So people look at machine learning as a subset of artificial intelligence in general. Okay, and this is something I suppose that you may want to look at. So here is an example about machine learning. What you are seeing is that I have about 6 observations. Each one is a sample of some animal I see on the well in the world. So this is a little bit funny example because what you see is not so realistic. But anyway, don't treat it so seriously. It's just a toy example. All right. So the first sample say an elephant is gray, is a mammal, is large, is a vegetarian, I suppose, and is live in the wild. So that's how you describe an elephant. And most of elephant you see have those characteristics, right? The second sample say that an elephant can also be a gray animal with he is also an mammal. He's large, but he is not vegetarian. He live in the wild. So it's like we have an elephant that it meat for some reason. Is weird, right? But who knows? Maybe there exists some sort of animal like that, and this is an elephant. Well, the third sample say if you see some animal with the gray color, also a mammal, but it's very small. It is vegetarian and it's live in the wild. Maybe it's not elephant. So take a look at those examples. What you see is that we we have a way to imagine about our data. Our data give us a bit of information about how distribution of the elephant occur in the wild. And so if you see how many possible cases we can have. So I have 1, 2, 3, 4, 5, totally 5 properties. Each property can be either positive or negative. So that's 2. And it gives you a sense like this. I have at most 2 power 5 sample. No, 2 power 5 possibility of observation I can have in the wild, right? And that number gives you about 33, no, 32 sample, okay? But now, in your experience, you only see 6 and more like that, and that's not enough information, right? So that's cause some sort of error in classification. And now, if you take a look at the predictions, ignoring everything we have so far, what you observe is that, all right, I need to predict if the sample 7 is elephant or not. And what you see is that it's gray, it's a mammal, it's large, and it's also not vegetarian. So that's the idea, and it's live in Y. Now the sample 7 is easy to classify because if you take a look carefully, sample 7 actually are similar to sample 2, right? Not similar, it's exactly the same as sample 2. So you may classify this one as positive because, well, it must be an elephant. Sample 8, we have this one is a gray, but not a mammal. Okay, it's gray, it's not a mammal, it's large, it's not a vegetarian, it's live in the wild. So, well, lucky for you, I found this in the training data. So, which means I can easily classify this one as negative. I can say, all right, this guy is not an elephant because the data says so. All right, but the last one, we have a gray mammal, or it's also large. It it meat. It's not very vegetarian, and it doesn't live in the wild. So maybe you can see it in the zoo, for example, or in the safari. Then will you classify this one as the mammal, sorry, an elephant or not? We have no information to classify here. It can either be positive or negative, and you have no idea what it is. So this is a problem of machine learning. The data may not cover everything you can see, and your new data that you have to classify actually not in the observation you have before. That is why we need to build a good machine learning algorithm so that we can classify the new sample. Okay. Well, given that idea, now without any machine learning algorithms so far, with your instinct, will you classify the sample 9 into mammal or, oh sorry, into elephant or not? What's your idea? Still elephants? All right. So you have a gray mammal and it's very large. It's not eat the meat. Yeah, it's live in wild. No, it's live in the zoo. Not eating. No, we have no idea. We have no clue, right? Because there is a case where vegetarians is elephants and not, well, that vegetarian here is not a factor to make decisions. Likewise, the why. You see that if you live in the wild, you can still be an elephant, right? And if you don't live in the wild, you can still be an elephant. So living in the wild or not is not the key factor. So again, I agree that from your instinct, you may say, okay, this one may be still an elephant. Who knows? We don't know. We have no evidence for that. And this is why we need to build a solid RMs right here. Okay, so thank you for your answer. So we may move on to discuss a few RMs later. So let's see, what is machine learning? This is a formal definition again. As you know, learning is an endless process of generalizations. So like no one teach you who is the boy, who is a girl, but because you look at the sample a lot and you make the conclusion of yourself, you build some sort of classifier inside your head, and you generalize that idea by saying, okay, if I see someone with the long hair, it may be, maybe, just maybe, a girl. and most of short hair people I see is a boy. And that rules you make is a generalization of what you see. Okay, so we call that generalizations or induction process, the same meaning anyway. We see a lot of sample like that, and we generalize that into a rules, and we call that machine learning. All right. So still, there are some error in that classifier, because nowadays, a boy can still have a long hair and a girl can still have a short hair. Who knows? But that is not the key factor. Again, so in machine learning, we classify the items into several categories depending on your viewpoint. So the first two categories you may encounter is supervised learning and unsupervised learning. Now, for supervised learning is a sort of items that require your training data to be level. What I'm trying to say is that you have to teach machine what is what. Like, okay, this is my cell phone, this is my wallet, this is my pen, this is my tablet, and so on. So you need to tell the machine what is that class of the thing you are seeing. Okay, that's supervised learning. And unsupervised learning is the difference. All you have is data. You have no other thing. You just have data. And your job is a little bit different. What can you learn from just data? Well, first, you may learn about distribution of your data. You may learn a similarity between your data, for example. After seeing a lot of people in your life, when you meet some people, you can easily recognize and tell, okay, this guy is familiar. He may come from China. And the other one is, oh, his face looks familiar. Maybe he looks like European guy, or oh, this guy's look like a U.S. citizens, something like that. So we classify people a lot without any label. Have you ever seen people label those things? No. But because you meet a lot of people like that, you, for some reason, cluster them into groups of people with similar characteristics, and then you only need a few hints. Likewise, for example, I know this group of people, they are very similar in a way, and then I know one of them, they are U.S. citizen, and then I can tell the rest of the group is U.S. citizen, something like that. That's unsupervised learning, and we will discuss a lot of items related to unsupervised learning also. Some of them is a little bit, how to say, not widely used. We nowadays have some other techniques, and most of techniques does not rely on the items we discussed in the course. But don't worry, because if you work out in some problems like molecular depth estimations or a lot of problem in computer vision nowadays will employ unsupervised learning. What I mean is you don't really need the data. You only need to tell how to evaluate the result, and the model will try to adapt and learn itself. So that's one way of unsupervised learning. Okay. And we will talk about that if we have a chance. So don't hesitate to tell me if you are interested in some topics, because beside what basic background we are discussing in the course, we also encourage our students to discuss something that is related to their research. So I hope that you may find some good information for your projects, if you will. Now, another groups of machine learning algorithms that you may encounter is reinforcement learning. Well, what is reinforcement learning? You may heard about it somewhere, and you may also see a lot of papers or videos about reinforcement learning for robots that they play football together. Okay, maybe that is a little bit out of the world, but really there are some lab they open some sort of competitions with other labs around the world just to play football, and you build agents. Those agents learn to play as a team to move the ball to the other side, the opposite side, and to get the score. So all of that agent you build is from reinforcement learning algorithms. Okay, and maybe this is a little bit out of our course, but hopefully, if you're interested in that, we will have a session to discuss. Okay, but you have to tell me before that because I need some preparations. Anyway, another groups of machine learning algorithms is evolutionary algorithms. Well, that's a completely different study field where they try to employ the idea from biology. You know, um, we humans and animals evolve so many times through from generation to generation. And what happens here is that when you evolve, how do we say evolve? Because you don't change yourself, but you change through your offspring, your child, right? Your grandchild. So that's the idea. You have a lot of people in this community, may you call it populations, and then there are some good individuals, some not so good individuals, and the nature say the good one will stay, will live on. The not so good one may not live for long. And then the good individuals, they may mate and produce the offspring. So the offsprings may inherit something good from their parents, and they may be better. Also, during the mating process, something may happen. Some some people that has very normal parents can become a genius or become superhero just because they have some mutation in their gene. All right, and yeah, they become better. So again, evolutionary learning means a groups of items that employ all kind of idea in nature and bring that from biology into computer field as an algorithm that help you solve the problems. Okay. Now, if some of you have learned about the course Introduction to AI, you probably know about this. But if you don't, then we have to discuss about it again. But yeah, don't worry. We have a session to talk about evolutionary learning. Well, in general, the most common machine learning algorithms you may encounter in the future will be supervised learning. And there are about two problems that most of you may encounter. That is classification and regressions. Okay. Now for classifications, given an instant, you need to classify if they belong to some classes that you know. Okay. And for regression, you try to predict the value given that. So, for example, you want to predict your stock price, right? And given some sort of input information, you want to predict what is the stock price in the next day. That's also a problems of regressions. Okay. Now let's see what we have. Uh, So this is something like a general concern. How many phases do we have in machine learning? Can you guess? It's a bit of a very general questions. I don't think it's easy to do so. But let me see. We should come up with some pipeline of machine learning and to see how we train the model as well as applying the model in practice. Now, what you see is that during the training process, it's unlikely that people give you the training data and you can just run the items right away. No, the training data will be used for training process. So you will do training, right? And you will get the models. But that model may not be the one that you can use right away. You have to pass that model into the testing phase. In the testing phase, you have the test data, okay? And the test data is something that is not joined with the training data. It's just something not in the training data. And the purpose of having testing data is that we try to see how good our models performs when it sees some new data. Okay. And if in the testing phase you see that your model perform not so well, then you may want to come back to the training phase and train the model again. Why? So maybe in the training process, you underfit your models. I should not say that, but looks like your model doesn't uh, achieve the performance you require in the training. Or maybe your model was overfitted. And in that case, it's fit with the training data, but not for the testing data. So we have to find a balance between training and testing. Okay. Now, even with the testing data, there's no guarantee that your model can perform well. So after testing and you see that your model works well on the test data now, then you may apply that into the real world. Okay, apply the model into the real world with the real data. And then during the applying process, you may gather some information. You may gather some sort of evaluation related to your model. And if it is so bad, you will come all the way back to the training phase and then train again. Because now the real data say, okay, your training data does not really fit with the real data. In other words, it does not represent the real data. Okay, so it's very important when you collect the training data. Your training data must somehow representing the real world data. For example, you want to do face recognition, okay? And a face recognition system require a lot of data, a lot of face. So you just took a lot of picture from different people and asking if that picture you took really represent the people you may see in the future. Okay, so for some of you, if you go to the shopping mall and you took a lot of picture of everyone get in and out in the shopping mall, then can you conclude that your training there represent every people you see? Probably not. Those may be just a group of people, maybe young, maybe a little bit wealthy. They have money, so they can have a very good face in some sense. But in general, if you go outside and you meet a lot of other people, their face may be different. And so the future can also be affected by your training there a lot. That's the idea. So hopefully that you remember the phase of machine learning in this diagram to apply later in your work. Okay. Now, there's some techniques we call K4 cross validations, and I don't recommend this one, even though some of you are still using. Well, what do you think about K4 cross validations? I believe some of you may heard about it or have been using it for a while. It's like this. You have data, okay, and you cut your data into part. Well, for example, in this case, 3 folds. And then you can use one part for training and the rest for testing. Well, maybe not, because this is a little bit unbalanced. Sometimes we use a lot of data for train and a bit of them for test. So maybe you prefer picking a part of your data for testing and the rest for training, because it's normal for me to choose a bigger set of data for training. Okay, and then this is one fold. For another fold, you will pick, well, you will pick this one for testing and the rest for training. And for another fold, you may pick this one for testing and the rest for training. So every fold give you a different models, and you will have different testing result. Okay, so you can take the average of those testing result and you say, okay, this is the average performance of my model given this K4 cross validation process. Okay, so that is what people do. But the thing is, this only apply for small problems. So if you have small data and small model in machine learning using simple items, you may use K4 cross validation. But if you work with some problems with like, let's say, uh, some problems that require a lot of well, data, and also it's a big model that require a lot of time for training, then you may not want to use this. The reason is clear. If you use this K4 cross validations, you have to spend a lot of time in training again. For example, if I have K4 with K equal to 5, and I have to train a model for 1 week, then in order to perform this K4 cross validations, I need, can you guess, 5 weeks of training. If I have more money, I can buy 5 to train. But that's insane, and no one do that. No one will do that. Okay, so keep in mind that K4 cross validation is only good if you have small problems with less data. But if you have a bigger problems, then this is not a good one to go. Okay. Now, there is another terminology in machine learning that you guys may consider. That is called statistical significant test. Well, this test is proposed to reject null hypothesis. Well, what is null hypothesis? Null hypothesis is the one that when you compare to system, you say they are equivalent in terms of efficiency. Okay. Well, it's hard for you to understand this sentence, I suppose. Well, this also a terminology that bothered me a lot when I decide to put it here in the slide. But I believe some of them, if you persuade the theory study of machine learning, you need to know it. It's hard to explain it in a very abstract context like this one. Okay, they say that null hypothesis means the hypothesis when you compare two systems and they are like equivalent, right? even though their performance measure are different. How to say equivalently efficient, even though the performance measure are different? Well, think about it. You may have a models, right? The models A give you the performance like 80% accuracy on the test data, the validation data, and one B model that give you the performance like 90% accuracy on the test data also. And then you bring that two model into the world to test, and you obtain similar accuracy in practice. This is art, right? That is why we need to reject those null hypotheses. It's saying that the way you train the models may give you models with different performance, but they are equivalent when you bring it out the world to test. You get it? Give me some sign. If my explanation is not good enough, then just tell me. I would like to clarify it a little bit here. But if you get that idea, then that's fine. How about that? Do you get what I am trying to say in this part? Or is still blurry?
Teacher, null hypothesis
Yes.
is a filter that affect the model or something else.
Can you repeat your questions?
So when we reject null hypothesis, when that's true model that's perform in the real world, so null hypothesis in this case is a filter that affect the model or something else.
The null hypothesis is the model itself.
It's the model itself. So we reject one of choose model pole.
So the statistical significant test imply that if you discover there are some models that give different performance when you train, but when you test it in the real world, they are equivalently efficient, then you should not trust the model because
So the problem is the data, or problem is the model itself.
yeah, the problem is the model itself.
Oh, okay. Yes.
So it's like you have model A and the model B. Model A give you the validation performance 80%. Model B give you the performance 90% of accuracy, right? 90
Yes.
and 80. So what we say is that if your data and your model work well according to the theory, then the model B that gives you performance 90% accuracy should perform better than model A in practice,
Yes. Yes.
right? But when you bring A and B to the world to test, they give similar performance. Then we say this is wrong.
Oh,
This is
okay.
not right, right?
Yes. Yes.
It makes no sense. Yeah, that's the
Yes.
idea.
So if the model B is perform better than model A in the real world, so we cannot have enough information to reject that.
Yeah, that's right.
Yes. Okay. I understand. Okay, thank you,
Okay,
teacher.
so I'm sorry that my explanation sometimes is not so good, especially when it comes to some abstract concept like this one. All right, so we have comments here. I heard that 70-30 is the common ratio when people split the data into training and testing set. How about order ratio like 50-50? I think it makes more sense to have equal size set. Well, interesting idea. Well, it's not about the size of the test and the train, okay? It's about the distribution. It's all about distribution. If you have a lot of data, the ratio doesn't matter. If you have very little data, the ratio may matter a lot. So what I mean is that when you have a lot of data, your data may cover the whole sampling space. Therefore, if you just take about 30% for testing, that 30% of sample already cover the the space of sample in the world. So it's made representing the distribution of the data in the real world. And so the ratio 70-30 is enough. Now, why people pick 70% of data? Because they want to train the model better. Again, we are talking about machine learning. And if you have more data for training, it's better, right? It is the fact. So if you have more data, you can approximate the distribution of your data better. And so people very often favor more training data compared to the validation data. Now, if you choose the ratio 50-50, then that's fine too. There's no one saying you cannot do that. But the fact is that, again, if you have very little data, and if you pick the ratio 50-50, then there is a risk that 50% of data you sample is not really cover the world, really representing the distribution of the world. Therefore, it's maybe a risk that you have to take. I'm not sure how it performs, but again, there is no evidence about a good ratio. No, we don't have that kind of evidence. All we have is just some experience come from the training process of different scientists. Okay, yeah, you're right. That ratio depends on the size of the data. If you have more data, you should choose the ratio differently. And again, I told you, this is just the heuristic. There is no rules in picking the ratio. Of course, people say if you have less data, then you should favor more testing data. If you don't have a lot of data, then the more test data you have may be better because that represents the distribution of the work better. And if you measure the performance on that test data, that gives you a better sense of how your model will perform in the real world. So when you have less data, then you may choose the ratio 50-50. But if you have a lot of data, then you may choose the ratio 70-30. Another reason why we do that is because if you have a lot of data and you pick 50% of your data just for testing, just to measure the performance of your model, you waste a lot of time, right? Actually, if you have a lot of data, 30% or even 20% of your data for testing is enough. But if you have less data, then you can spend more of your data for testing. That's the whole idea. And you're right. You say that the size depends on the ratio depends on the size of data. That's the correct statement. No, statistical significant test saying that when you do training and testing, you should be careful because sometimes you may have models training with different performance, but when it perform in the real world, it gives the same performance, and that is wrong in terms of theory. So you may revise about your model again to see what is wrong. Why there is something inconsistent between the training phase and the testing phase. By testing, I'm saying testing in the real world. Okay, so that's the whole idea. So are we clear about this one? Okay. So hopefully that you should check this one later. If you're still concerned about it, tell me. I will try to explain about it again. Yeah, it's a rule to keep in mind. Okay, not a rule. It's just some sort of principle that a lot of people should be aware of. All right. So you will very often see some sort of diagram like this in your life when you train models. The orange color is the testing result, and the blue line is for training. Well, it's actually the value of the loss function. Okay, and why do we bring this one up? Because as you can see, at the beginning, your loss will drop down very nicely. Okay, and don't expect that the line will be a smooth line. No, during the training, the loss may change and varies a lot. So we may see the glitch in the loss function a lot, but the trend is that it's going down. But the problems now is that for training, you can see that the trend of your loss drop down. Why? For testing, the trend goes down, but then it goes up. Okay, because here at the point here, you will see that it's like this is somewhat an optimal range. When you train the models, you would like to keep in mind that if you train too much, it's not good for your models, because your models now, even the loss of training is dropping down, but the loss of testing grow. So that means your model was overfitting. Okay, and if you train but your testing loss can still drop and you stop earlier, then we call this part is underfitting. This happens very often in practice, because as you can see, well, when you do a lot of training, especially for big problems, one epoch may consume about like 1 day just for one epoch of training, and that's a lot of time consuming, right? And so some of you may lose your patient in the very early days. You train 1 or 2 days and you outpatient, you just stop. So if you don't observe this lock, you may be in the situation where your model is underfitting without awareing of that. Okay, so be careful. Very often, if you are dealing with some small problems, maybe you don't have underfitting. Most of the time, you are going to encounter overfitting. All right. Now, so why we care about overfitting? Because in your data, there will always be noise. Always. You cannot avoid that. Okay. Noise is something very often appear in our world. For example, when you go out one day and you meet some people, it's just easy for you to misread that person. You may consider that one to be a male or a female, and the thing is, you don't know if you read correctly or not. But yeah, you have to keep in mind that sometimes we have some wrong label on things, and because of that, that sample you are seeing is a noisy sample. Okay, and if we mislabeling the data, or we have some wrong idea about the data, you will feel very bad. Or for example, I can tell you like this. So let's say this are male, okay, and these are females. For most of time, male and female stay away from each other because it's easy for us to recognize. But then there are some people are very close to female. Okay, there are some female are close to male. Actually, these two sample are male, and those two sample are female. No, I I'm a little bit confusing here, so sorry about that. So let's say this X of the cream is a female, but I mislabel it as a male, and this one O is a male, but I mislabel it as female. All right, so very often I have noise like this in my data. And then if you build a perfect classifier, can you do that? Yes, you can. You can always build a perfect classifier like this one, but then this one give you 100% accuracy in the training data, but it does not perform well in practice because what actually happens is I prefer a classify I'm sorry. I prefer a classification rule somewhat like no. That's bad. I prefer some classification rules like this one. Okay. Well, this may work better in practice, right? Even with the noise present in your data, this still works so well. Okay. So the idea here for overfitting is you don't need the best accuracy in the training data. You don't need, because your data may be noise. Yeah, maybe it's very noisy. So you don't have to overfit on your training data. That's the idea. Okay. So speaking of machine learning, you have to talk about some performance measure. And those performance measures here are something you see very often. So I'm going to repeat this one, even though you guys may know about it. So in machine learning, we have some concept called true positive, false positive, false negative, and true negative. And you have to remember what it means and why do we need all of those things. So true positive means that one is the one you want to classify and is correct. Well, this is hard to tell, but let's say positive means you got disease, okay, and negative means you don't have disease. So the left side is actually people who got disease, okay, like diabetes, for example. And the right side are people who just normal, they don't have diabetes, okay. So given all the information, given all the record, you build a classifier, and some of them you say, okay, those guys are having the diabetes. Then those people who got disease, and you tell them that they got diabetes, then they are true positive. Okay, and those are some people who actually got disease, but you say no, you don't have diabetes, then they are false negative. right? They got disease, but you say they don't have, then that is false negative. So the second one is actually your decisions. And the first one is the property of your decisions. So you say they don't have disease, but you're saying it's wrong. That's called false negative, right? Likewise, on the right side, if you classify that one as normal people, doesn't have any disease, then uh, that means you have true negative, because the one actually doesn't have any disease, and you say, okay, you don't have any disease, so it's true negative. But if some people who doesn't have disease and you say, okay, you got disease, then that calls for positive. All right. So those are concepts in machine learning, and we utilize this one a lot when we measure performance of some models. Okay, so here we use precisions and recall a lot. Precisions is the number of correct system answer given the number of system answer. Okay, that's precisions. So can you tell? It's gonna be, well, how about number of correct system answer? True positive plus true negative, right? The total number of system answer can be true positive plus true negative plus false positive plus false negative. All right, that's precision. That means how many percent of your answer is correct. That's precision. Well, if you only care about the accuracy, then well, there's some confuse between the precision and accuracy. Okay, so what I'm writing more like accuracy, not precision. Well, when you talk about precision, you have to talk about the precision when you predict something. For example, I'm talking about precision when I predict the positive cases. In other words, I say, yes, you got the disease. Then what is the precision of having the class yes? Then that means it's true positive over true positive plus false positive. That's precision. Okay. What about recall? Recall is the total number of correct system answer over number of correct problem answer. Okay, so it's gonna be a little bit odd. So I think you need to read the formula here to see very clear about what is there. So as I mentioned earlier, precision is the number of right answer over the total number of answer you have. All right, so that's precision. What about recall? Recall is the number of correct answer over what? Over the number of relevant answer. This is a little bit odd compared to what you have known so far. Now, if you take a look at this one, if you compute the precisions, then it's gonna be true positive over true positive plus false positive. So it's the the green color divided by the whole circle, right? Divide by the whole circle. But when you talk about recall, you take the true positive, you divide by the whole square. This is recall. Okay. So recall means among those people who got disease, how many percent of people can be classified correctly? Okay. Why accuracy say among those people you say they got disease, how many percent actually got disease? Okay. So if you say your system give the precision 100%, that means I don't care. If I say that person got disease, 100% of people will got disease. Can you have a system with precision 100% and recall 0? Can you have that? I'm just raising questions. So may you tell me, can you have that kind of system?
I think yes.
Okay. Yep. Can you tell me?
I think no, teacher.
No?
Yes.
Actually, we can. We can build a system with 100% of precision and 0 recall. And also we can build a system with 100% of recall but 0 precision. It's very weird, but yeah, it's true. Check it again about the formula.
Teacher, can I ask a question?
Yep, you can.
Because for example, if the model predict only one true positive,
Mhm.
so the recall maybe it's too small, but it can be zero. I think so.
Okay. Yeah. Can you repeat again about your questions? I
For
cannot hear
example,
it.
if the model have 100% of prediction or precision, so it has, for example, one prediction, and that prediction is true.
Mhm.
So the recall maybe it's too small, but it can be zero.
All right. It cannot be 0, as you mentioned. All right. So it depends a lot on the concept, but well, speaking of precision and recall, there are a lot of debate about those things. Well, we need to be very skeptical. No, very careful about this information. You cannot rely solely on precision or recall. Both of them are lying. So you have to find some sort of balance measure between precision and recall. Because look at the situations. Suppose that you have very high accuracy, no, very high precision system. When you say that person's got disease, then precision is 100%, right? If you say that person doesn't have disease, then 100% that person doesn't have disease. Now, let's say I am building a machine learning system and I say no one got disease. What is the precision of no? You cannot tell, right? You cannot tell. That's a problem we have when it comes to such situation. So let me see. I'm trying to figure out a good example for you in this case. Let me see. Oh, we have one friend have answered. So if one is 100% and other is 0%, then true positive is differ from 0 first, and true positive is 0 equal 0 second. Is this possible? Yeah, I know. This is something we care about when we talk about precision and recall a lot. So this is why you have to think about this example. Okay, hold on. I'm looking for a good example here. Let me think a little bit, just a moment. Okay. Let's see. I remember a long time ago I read in that books. I have found a good example for this one. I think I have that one. We call that edge case. Let me see. I'm thinking about that example a lot, but sometimes I just forgot. Let me see. It should be a good example if I recall. Mm. Mm. Okay, so let me say this. Suppose that all the sample you observe is classified as negative. What happens? What happens? If I say no one got the disease, what do you think? If no one has a disease, then the number of positive sample and the number of negative sample is 0. So what you have here is true positive is 0 and true positive plus true false positive is 0 plus 0. So you got precision 0, 100%. But for recall, I say everyone has no disease. I say no one got disease. Negative. Then what do you think? Recall is 0, right? Why precision is 1? Make sense? If I say for every sample you give me, I say everyone is fine. You don't have any disease. What do you think? In that case, true positive is 0. True positive plus false positive is also 0. So your precision is 100%. And recall is 0. Is that true? This is what we call edge case. Some special case. Now, when you do software testing, very often you see some sort of cases like this one, right? But maybe you didn't aware of that. The reason why I didn't think about this example at first, because it's very weird, but it may be possible, right? You can make a system and say to everybody, you guys are fine, you don't have any disease, and your system has precision 100%, but recall 0. And you can also build a system that's saying everyone got disease. And you say that, what happens? Think about it. All right. It's just an example, but I hope that you get the idea. Sometimes you can get a system with precision 1 while recall is 0. So this is why in machine learning, you may not trust either precision or recall, but sometimes, in most of case, you have to rely on both of them. Okay, so that's the whole idea of having precision and recall in the formula. And this is why for a lot of problems in machine learning, you guys will use F1 score instead of using precision or recall. In fact, precision and recall are just some way to, well, what can I say? Uh, use as a reference, okay? But by no means you should trust them. And they use F1 score. F1 score is actually a harmony average between precision and recall, just like you see like that, okay? And yeah, hopefully that will bring us to a point where you can apply those technology in your evaluation, okay? Now, when you talk about machine learning, you have to talk about one concept called inductive bias, and a lot of people don't aware of this one. Maybe you guys don't even care, but this is so important. So let me ask you this example. What will you do? What is your decisions when you look at example 3 and 4? Now, of course, when you go to shopping on either the e-commerce website, or you go to the shopping mall, or you go to supermarket or whatever, you will choose some good with good price, right? And also good quality. That's the thing you make decisions. So if you see something with a good quality and the price is low, you buy it, right? For sure, no doubt. And if you see something that is so ugly, so bad in quality, but you still check the price. Now, the price, if it's so high, then obviously you don't buy, right? So if a bad quality product with a very high price, obviously we make a decision no. So given those data, what will you do when you see um, a good item with a high price? What do you think? What do you think? Some of you may say, okay, I will buy if that is a good product, even though it is very expensive, because I favor good products over the price. But some people say I don't have much money, so even if the product is very expensive, no, sorry, even if the product is very good in quality, but it's too expensive and I cannot afford to buy it, I will say no. So each of us may have different favor, right? We bias to different factor, okay? And only when we have bias, we can make decisions. So in machine learning in general, if you don't have bias, you cannot learn anything. And that's the key. That's the key, right? Remember, you have bias and you can learn. If you don't have bias, you cannot learn anything. All right. So here, for example, 3 and 4, you may not make decisions. Some of you may make your own decisions based on your favor. Okay, may you favor the quality, may you favor the price, but only if you favor one thing over the other, you can make decision. That's the idea. And So they have a statement like this one, and it's very important. It's saying that a learner make no prior assumptions regarding the identity of the target concept cannot classify unseen instant. That's exactly what you see in the example earlier. What is the prior assumptions? Some assumption that you have even without seeing the data. Okay, for example, you may say, okay, amongst all the good I see in the market, 20% of them has a good quality. Okay, that's the prior assumption. I know the probability of good items is 20%, and the probability of bad items is high, 80%. That's prior assumptions. So that the distribution of the data. Okay, and also there are some other things that you may consider. So what I try to tell you is that we have the assumptions. Okay, given an item, you may not know if that item is good or bad. You don't know, but you know that 80% of chance the item is bad and 20% of chance the item is good. That's prior assumption. Okay, and for so many problems, we need to take that into account. Okay, and if you don't have those prior assumptions, you cannot classify the unseen instant. That's the point. Okay. Second, the statement say that a learner makes no prior assumptions regarding the identity of the target concept, has no rational basis for classifying any unseen instant. So this is exactly what we just say in the example. If you assume that a good items is the one to buy, okay, and that's your favor, then you will buy the good item regardless the price. But again, I don't think this is a good example because we have to bring the number into the table, right? So right now we didn't calculate a lot of things, so don't worry. I will come to that part in the next lecture. Not yet. Now, last thing. This is the definitions of inductive bias or learning bias. Inductive bias is a set of assumptions that the learner used to predict the output given the input. Okay. A set of assumptions depends on the algorithm you are using. So if you are using some techniques in machine learning like Bayes, for example, then you have to make assumptions that all the attributes are conditionally independent from the class. So that is inductive bias. Okay, so it's a set of assumption. Okay, and keep that in mind whenever I discuss about inductive bias. You have to remember those are some assumption we make when we propose the model. Well, for example, here I will list a bit of machine learning models and what is the inductive bias in those models. So first, you see that for Bayes classifier, we have the maximum conditional independence. In other words, you want to find a class. The class C is supposed to be the argument max over every class of probability of the class given the data. Okay, so what you're saying is we try to maximize the conditional independence. We say that in the Bayesian framework, we try to maximize the dependency between properties. So what properties you have here? D. Well, D is your data, right? Your data has several fields. And so this one is equal to the products of over I equal 1 to n. And this one is equal to P, C given DI. So from here to here is conditional independence assumption. It's saying that the probability of C given D1 to Dn is equal to the product of I from 1 to n of P, C given Di. So this statement say is the conditional independence. The independence under condition of class C. Okay. It's not that easy. It's not simple like this one. What actually happens here is that we have to simplify things a little bit. What little bit? It's not going this way. It's going a different way. It's going like this. This one equal to argument max over class C. We not write this way. This is wrong. The right thing to write is this. This is the argument max of P, the data given the class, multiply with probability of the class. Of course, you have to divide by the probability of your data, but that doesn't matter when you take the argument max. So I make a shortcut. I take them out. And now this one is the prior of the class. So in other words, it's the distribution of the class. How many percent can you observe the class? And what is this? This is the conditional independence. P of D1 Dn given C equal to the product of I from 1 to n of P Di given plus C. And this is what we call likelihood. Okay, so a lot of concept you may encounter later, and we will back to this point when we discuss about the neighbor yes classifier. So don't worry, we will get there. The second one is called minimum gross validation error. So we choose among hypotheses. There are a lot of hypotheses, and you have to pick the best one. So that's exactly what happens with K4 learning. Okay, great K4 cross validation. And the next one is the maximum machine. So in this text, what we do is we try to maximize the distance between two classes by set up somewhat a classifier that can maximize the machine between two classes. Okay, in this case, it's going to be supervised machine. And we will have a lecture on supervised machine, so don't worry. And we have the minimum description length. This also another hypothesis that a lot of people prefer to use. But it's just a little bit early to talk about this one, so let me skip that one. And also, you may want to find the minimum number of features that is useful for classification. For example, if you go to the hospital and take the measurements, do some health checkup, you got a lot of numbers in your health record. And in order to classify if you got any kind of disease, the doctor will base on some numbers, not every numbers you have in the record, in the health record. And so the doctor based on the minimum number of features have in that patient record. In short, what we see is if you have an input with a lot of data, not every data is meaningful for your problems. just a few of them. So you may want to reduce the number of features that is meaningful in your classifier, and then you use the technical minimum feature. Okay, we will talk about that when you have a chance. The next one, inductive bias, is an assumption saying that if the distance to a sample is close to some other sample, the one that closest to you is actually the one that gives you the information about the class you are. Okay, that's how you classify. And that happens with some system like face identity recognitions. You know, we have a face taken by the camera and then we feed that into the system to extract some sort of face feature, and those face feature will be compare and measure the distance with some face feature you store in the database, and the one closest to that give you some sort of information about the face you are seeing. So if the distance is small enough between one face to the other, then you say, okay, this is the right person in the database. But if the distance is larger than some threshold, then maybe not. Okay, but you are going to specify what is this man be based on the distance between the feature. Okay, so you use the techniques nearest neighbor. And let me see. All right, so that's some inductive bias for machine learning. I think that we can stop here because I just give you some other explanation about extracting layer, not in this one. We can go on to the next lecture if you don't mind. So let's see. I'm going to check the next lecture. It shouldn't be so quickly, right? Because according to the plan of the course, I would like to discuss with you guys two parts. The first part is traditional machine learning algorithms, and the second part gonna be um, deep learning. Okay, so hopefully that we can cover all kind of things in the course. And so I will run a little bit faster. So may I ask if you learn about um, decision tree? Okay, we have a question here. Does machine learning really learn, or it just process data by following an algorithms? Well, it depends on what algorithms you are using. Some machine learning algorithms does not really learn. Some machine learning algorithms learns. So your question is, does machine learning really learn? That is very general questions, really. Uh, my answer for you is yes. Machine learning algorithms, in most of case, is learned from the data. Okay, and the algorithm is just a way to train or to teach how to learn. You may write some specific algorithms, but that's to tell the algorithms, sorry, to tell the model how to learn from data. All right, so I guess that we should talk about the next topics, but I wonder if you guys are very familiar with this topic. It's called decision tree. How many of you didn't learn about decision tree before? Sorry. Raise your hand if you haven't learned decision tree before. One, two, oh, quite a bit. All right. So maybe we have to do this job. I think I can skip it, but maybe not. All right. So I will give you a quick introductions about decision tree and why it's matter. Well, decision tree is actually very basic algorithms in machine learning that people use a lot. And even though it's so simple, it's still the one that you have to look at because some systems still use decision tree, you know. It's not something outdated. No, we still use it until this day. For some problem from simple to complex, so it depends a lot on situations. All right. So in this lecture, we are going to talk about decision tree learnings and how to construct them. Okay. Now for decision tree learning, you will see that there are a lot of algorithms, but most of them come from the basic, like TDI, right? Top-down induction decision tree. And we will talk about those algorithms first. And most common and most widely used decision tree algorithm is ID3. So it's tell you how to select the attribute, how to measure the information theory in decision tree, and also we have some advanced discussion about C4.5. So I will save it for the next class, but don't worry, we will talk about the basic one first. So for decision tree, well, this is what happens. Well, I guess I should clean this one up. This is from the previous lecture, not this year, last year, I suppose. All right. So decision tree is a tree. Yeah, it's a tree. It consists of node and leaf, right? The nodes say, well, this is the node with some attribute, and this is the branch with some attribute or attribute. And if you end up here, you may have the leaf. So the leaf actually class 1, class 2, class 3, and this may end up with class 1, 2. This may end up with class 3, 2. So the thing when you take a look at decision tree is that it's a way of classifying your data based on the comparison on the attribute. Okay, so it consists node, edge, and leaf. Nodes are some node in the tree, of course, and it's representing an attribute. So you compare an attribute in your data with this node and decide to put it on the left side or on the right side. Well, actually, we may have many branches. It's M-way tree rather than binary tree. Okay, the edge representing the path from one node to the other, and the leaf represent the terminal. In other words, you don't need to compare. All the sample in this groups will belong to one class, a single class. Okay, so it's make the decision rules. All right, so that's how we have decision tree in general. You have that concept, and I believe it's very easy to understand. So you take a look at the common decision tree. You have a lot of data, right? And you construct the decision tree based on the training data to build a tree in the middle. And for some new sample, you have to make decisions by comparing the attribute of your new sample with the node and decide to go in some subtree. And then finally, if you end up with the leaf, you make decisions. This is the class of that sample. Okay, pretty easy. And so here is an example that I believe all of you may take a look earlier. somewhere. I don't know, but let's see. All right. So we have a recorder of someone who play golf, right? And he make decision either play golf or not based on the temperature, based on the outlook of the weather, the humidity, and the windy conditions. So for temperature, there is three values, either hot, cold, or mid. For the outlook, there is sunny, overcast, or rain. Okay, three value again. For humidity, there is three level: high, normal, or low. Okay, and for windy, you have about two values, either windy or not. All right, and we have to make decision either to play golf or not. Those are training data. And given those training data, you see that we have some sample. For example, today, the temperature is cold, the outlook is sunny, the humidity is normal, the wind is false. So you have to make decision whether to play golf or not. And if you take a look at our training data, we have found something similar, I suppose. So it's gonna be cold, sunny, and normal and false. So looks like we found a match of today record with the play golf, and you can easily answer this. It's a yes. But for the next sample, maybe not. Mid, sunny, all right, mid, sunny, normal, we don't have. It's the mid, sunny, normal. Oh, this one. And false, no, we don't have. So mid, sunny, normal, nowhere to be found, right? So you cannot make decisions for the sample tomorrow. And this is why we need training. We need to base on our data to make a decision tree. That decision tree is not necessary to be 100% correct, but it helps you to classify tomorrow based on the common sense, the statistic of your data. Okay. Right. So it's going like this. After training, you may have some decision tree like this one, and if you try to predict tomorrow, you will have the outlook to be, no, first we check the outlook first. The outlook is going to be sunny. Therefore, you run to this path, and the humidity, this time we check the humidity is normal. So you drive to this part, and your immediately decision is yes. You don't have to compare anymore. So that's the benefit of decision tree. If you guys are learning decision tree in the introduction to AI class, then it's just the same like this one. Okay. Now, let's talk about the most famous algorithm for decision tree is divide and conquer algorithms. Okay. The first one has a name. It's called TDIDT. We go from the top to the bottom of the tree. So originally, you will have a big set of data, and then in those data, there are some sample belong to different classes. So you want to measure the chaos, or in other words, um, the entropy of the data. So this relates to a course called information theory, which you didn't take, but that's fine. You may heard about entropy in some other course in math, I believe. So we will utilize that measurement in order to divide your big set into smaller one based on some attribute. And we keep divide our subset into smaller subset until your subset remain pure. A pure set is a set with single class. Okay, so that's the idea. Now, given that you can have the ID tree items, and this is what you have with ID tree items. You have a set, okay, and you you choose an attribute A according to some heuristic functions, and given that attribute A, you will divide the set S into some subset, and you keep repeating the process until your set is pure. That's all. That's all the idea of ID tree items. And I believe some of you can write this item by yourself if you want to. So this is a particular decision tree. Now you see that when it comes to decision tree, there are some cases which is very special. When you build a decision tree, there are some branch in the tree that has no data. In other words, you don't know what decision to make here. As you can see, we have never seen a sample that has the temperature is hot and outlook is rain. It's very weird, right? You have never seen something like that. So the leaf of this branch in the figure is empty. What kind of decision do you make here? Well, some people say if I cannot make decisions, then I rather answer I cannot make decisions. Okay, so that's what machine learning does. And for example, you have another branch. The temperature is cold, the outlook is rain, and humidity is high. You have never seen something like that. So in this case, again, you cannot make decisions. We are going to deal with this one later, not now, right? For now, when you build the decision tree, you have some tree like this, that's all. And if you cannot make decision, you cannot assign a class into a leaf, then just say, no, I cannot answer, I don't know. Rather say, I don't know, than saying that this is yes or no, okay? That's the main point of decision tree. And again, as I mentioned, this relates to information theory. We use some measurements called entropy in order to measure the unorderedness of the data. So look at the data. If you have a lot of sample of the class A and class B mixed together, then is that order or unordered? So if your set only contain the class A or only contain the class B, then the entropy of that set is, yeah, you know, zero. In other words, there is no chaos in entropy in your data. There is no chaos. Entropy is the measurement that measure the chaos in your data. And if your set is pure, there's no chaos, and entropy is zero. And the entropy is maximum when there is a half of your data is belong to class A and half of your data belong to class B. Okay, so that's the idea. Come from information theory, and these are something I I wrote earlier for my students. So it's going like this: you have an attribute A from class S, and you use that attribute A in order to divide your data into some subset A1, S1, S2, and S3, right? And for S subset, you may have the portion of the data, okay? And given that, you can easily measure the entropy of a set by the formula I put down here, as you can see. Entropy of the set S equal to the negative log of P log P, okay? Where Pi is the portion of the class I in your subset, in your set S. For example, if you have a set of three classes, A, B, C, right? And the probability of the portion of the sample of class A, class B, class C is 10%, 40%, and 50%. Then you can have entropy of S equal to sum of negative of 0.1 log 0.1 subtract with 0.4 log 0.4 subtract with 0.5 log 0.5, and that's the thing. Okay, I don't want to bring up the math too much because this is trivial, so let's just skip it very quickly. And as you can see, the distribution of entropy is reached the maximum when, well, this is the entropy of two classes problems. You have only two classes, either positive or negative. So if the class positive and negative are equally distributed, then you have the maximum chaos. If you have multiple class, then the maximum of entropy achieved when all the classes are equal. I mean, the distribution of all class are the same. If you have four classes, and that means the entropy will reach maximum when the probability, no, may I say, the portion of sample of each class is 20%. Okay, so that's how we care about entropy. All right, so just keep in mind that entropy is a number that measures the chaos in your data. All right, and in short, what we want to do is picking an attribute A, so that the attribute will either maximize or minimize something. But what you are seeing now is we measure some sort of information. We call that information gain from the attribute 8, or not gain, sorry. We call that informations of the set as given attribute A. That's equal to the average entropy of every single set divided by attribute A. Okay, so from set S, if you use the attribute A, then you can divide S into subset Si. And the absolute Si you are seeing there is the volume of the set Si. All right, so it's nothing but the average weight. Okay, no, weight average of entropy of subset. Okay, and you take the argument means of the attributes. It means that you measure the information of S over every single attribute A, and you pick the attribute that can minimize this information, because what you want is to pick an attribute that can make your subset to be pure as possible. So you may want to minimize the entropy of your subset. All right. Therefore, ISA is supposed to be minimized by attribute A. And again, what you are seeing is now the attribute you are going to pick is the argument means of ISI. Okay, ISA, sorry. And so we may want to define something called information gain. Well, this information gain is nothing but the entropy of the original set subtract with the information from select attribute A from S. So again, as you can see, if I pick the attribute A based on minimizing the information I, then it's equivalent to maximize the gain of S over attribute 8. Okay, and that's the same. That's exactly the same. So these are some note on the entropy, and you guys can check it later. I guess we can stop here now, and I will continue from here next time. So I'm sorry that I have to bring back the theory about decision tree. I suppose that you guys learn about it in introduction to AI course. But if you don't, we have to discuss how to calculate it. It costs some time, so I will spend time with you next time, and we will discuss how to calculate this. Okay? Are we good? Is there any questions you want to ask before we finish?
Teacher,
Yeah.
how you assessment us in this course? There's any assignment, midterm exam or final exam in the
All right. All right. I got the idea. So in this course, we have the midterm consume 40% of your grade, and the final consume 60% of your grade. That's the syllabus say, and there is no assignment. So assignment is some sort of bonus. So because you don't have so many people here, I want to ask if you want assignment or not. It's gonna be a bonus. What do you think? Do you want to do some projects of machine learning?
I think yes. Bonus is good for us. I think so.
But
All
can
right.
I ask a question? Can I ask? That's what is the what about the topic of the assignment?
So the
If we have
topic of all right, all right. So it goes like this. I want you to be creative in the course. So I'm going to, if you want assignment, then I'm going to post on the VCal some topics, and you guys can choose among those topics. And you need to perform some sort of study about that topics, do some implementations or evaluations on the topics, and write a report. That's what I want. Okay. And if everything goes well, you will get some credit for that job. Okay. And I think, how many percent should I bonus you? 20%, is that enough? What do you think? It's for your effort. Of course, you may not get all the credit for that assignment, but if you do it well, then you can get that score. Anyway, remember, for this course, the assessment is 40% of midterm and 60% of the final. And if you perform the assignment and you do it well, you will get some bonus. The maximum bonus is 20%. Is that okay?
Okay, teacher.
Okay. So in reasonable, I think it's a little bit high, but it's for your effort. So I think it is reasonable too. All right. So it's a deal, right? I will post the information about assignment later. It's yes, it's count as a bonus. So unofficially, but I will add that bonus into your final grade. For example, if you got the final exam to be 8, and you get okay, let me type it out for you. Suppose that your final exam is equal to let's say 8, okay, and you got the assignment to be 10, and your final exam equal to A plus, because that bonus is 20%, right? So you get 20% multiplied with 10 multiplied with 60%. Okay, so it's gonna be 9.2 in the best case scenario. Is that okay? So I will distribute the score of your assignment into the final exam as well as the midterm exam according to the ratio. Is that fair? Any
Yes,
questions?
sir. So the assignment will be the teamwork or individual?
It is supposed to be individual works, not teamwork. So I hope that you can try it on your own. Okay? It should not be too hard. The purpose of that assignment, is to give you a chance practicing the machine learning algorithms on some particular problems. It's unnecessary for you to invent something new, but at least you need to understand very well about the tech that you apply, and also you should learn how to evaluate your result. Okay, so that's the effort you pay for the course, and I will reward you by this formula. Is that okay?
Yes, okay, teacher.
Okay, so I hope you do well in the course, and we have a deal. So don't worry, I will release the information about exam later. Okay.
Teacher
So
can on the slide
yeah,
later on the
yeah, I
weekend.
will upload the slide for you guys. I will
Yes, thank you.
upload the slide to BK. Okay. So thank you for joining me today, and see you guys next week. I'm sorry that we cannot meet offline. I would love to. Okay, see you guys later.
See you later, teachers.
Okay, bye bye, teacher.